On that, and that's that note. I was supposed to be here on Tuesday to give the first lecture that Trinko gave, my first lecture. I'm Griffin Foster. Last year, I taught some of the courses with Trinko, and then I disappeared. I'm back for a bit, so for the rest of the month, basically, I'll be teaching. What will we be talking about? So on Tuesday, we talked about kind of spatial frequencies and imaging, the Fourier relationship to the UV plane and image plane. Today, we'll kind of continue on that in terms of how that applies specifically to interferometry and aperture synthesis. Then next week we'll talk about deconvolution, which is kind of the extension of imaging and kind of spatial filters. And then there's a CASA tutorial, which Sandeep does, or Sven?
They do it jointly.
Okay, there'll be a CASA tutorial next week also. And then then also do a lecture on instrumentation, radio arrays, and how they actually work in a practical sense. Was there any questions about last week? Or not last week, last lecture? Everyone on top of it was in love with it. Thought it was great.
He had a question that I want to bring up again, the discontinuity field.
Now in your slides.
Yeah. Do you have these slides here?
Yeah, I do. Sorry.
Yeah.
Just when you have an oscillation, you can follow it from positive to negative, but in the middle of it, it doesn't go through zero again. It goes to the ultimate positive, and then it starts from negative.
Right.
So you can see there's a discontinuity.
Okay, right.
It still gives the effect of the resolution. But
Yeah.
should be a blue line somewhere between the thing.
Yeah. We actually go down a bunch of slides, I think. Stuff like this, or
All of them actually.
what's that?
All of them.
Yeah, so before there's a discontinuity, but I think it's just because of phase running.
There's a discontinuity.
So it does.
It's easier if you have rougher resolution.
To follow.
So, for instance, you start at red, which is the most negative. Then it is, let's say, you go this way.
Yeah.
It moves plus negative, this negative, and then here, zero.
Yeah. Starts over zero, right?
Yeah.
But what do you mean?
I mean, you can't go from a positive value to a negative value without going through zero unless there's a discontinuity.
Well, you can if it's the phase, right? So it's actually, it's not quite, right? Not negative, it's that, or well, it goes from pi to minus pi. And
So it's
when you do the sine or the cosine of those values, it's cyclical, right? And that's why you don't have to go through zero. Because, right? Minus pi is the same as pi if you do the cosine or sine of it. Maybe I should make that more clear. That's a good point. That the whole idea of phase is that it's because it's cyclical. There's oftentimes degeneracies that arise under it. Okay, I'll consider how to improve that.
Oh, sorry.
So, if I recall from not giving the lecture, but remembering what's in it ends with discussion of sampling space, and you guys did a little homework thing on that, hopefully, about the triangle sampling function, producing the the PSF response to that and applying evolving that, right? Does that go well enough? Yeah, easy enough? Okay. So that's, I think all on Tuesday it was all quite theoretical in a sense, and that wasn't really practically applied to radio interferometry. So I think today we'll talk about kind of going to real interferometric arrays, kind of the issues that show up with these sampling functions, how they're not as simple as they appeared on Tuesday. So we'll talk about how weight functions work, how you kind of re-weight a lot of sampling if you oversample or undersample stuff. Talk about gridding. So one thing that kind of we avoided in the last lecture was that when you have an interferometric array, it's not as if you're sampling on a perfect grid, whereas the examples we showed on Tuesday was, it was a 512 by 512 pixel image. Each pixel was either black or white for the sampling function, but in reality, these UV tracks sweep through and they're not necessarily on the grid. So how do you go from kind of this continuous nature of the UV tracks to kind of a gridded layout? And then the last thing is we'll talk about this idea of what's called the W term effect, or the wide field effect. So it turns out, all this stuff about Fourier transforms, which are incredibly important to this whole game, is just an approximation, right? This approximation breaks down, and how do we take that into account in terms of imaging and deconvolution and doing science with it? And there's a number of tricks you can use, and it depends on the science case you want to that you're working on. Okay, so kind of the crux of it, to go from this theoretical lecture we had on Tuesday to kind of more practical application, is that there's this UVW space, of course, that that you guys have heard about in the lectures. And you have these tracks sweeping through. If you think of this as a 3D volume, each UV track is different. And it's not laid out perfectly on a grid, it's just continuous. And in order to do, if you have an irregularly sampled signal, the absolute correct way to do it is you apply the direct Fourier transform, the discrete Fourier transform, which is computationally really expensive. So if you have n samples, it's n squared operations to do that computation. And if n is big, n squared is even bigger. But if you can do this thing, if you can do a fast Fourier transform, you can get that down to n log n, and that's a much more reasonable size. And so our goal is to go from this irregularly sampled visibility space to a regularly sampled in some sense, to basically chop up this volume, this kind of continuous volume, into discrete chunks, and then you lay out the visibility power. You redistribute the visibility power somehow. That's called gridding, and that's by far always in interferometry the most computationally expensive task. Gridding, and then there's kind of a inverse operation called degridding. They're very different implementations, but they are kind of inverse solutions. Computational operations. Okay, so yeah, fast Fourier transform. The homework, this bigger homework assignment, hopefully. Has anyone done the bigger homework assignment, this implementing a fast Fourier transform? No. It's kind of, is that hard? Is it easy? Have you looked at it? No response. How many people have looked at it? 1, 2, 3, 4. You did, right? Because you sent me. Did you?
Yeah.
But you didn't look. So 4 people have looked at it, but no one's done it yet, right? So, what's that?
It looks easy.
Okay, if it looks easy. Yeah. So, definitely. So this is the first year we've done this assignment. Let me know if it's too easy, too hard. If you have any questions about it, please email me, because it's really a good thing to learn. Years ago now, I was sitting down with a professor, and he was talking about how, he wanted to learn a new programming language because he'd been learning Pascal or something, right? right? It's some outdated language no one should ever write in. And he wanted to learn Python. And so kind of something he learned years ago was he's like, you sit down, anytime you learn a new programming language, you should write out something, an algorithm that you know. And so for him, it was writing out the fast Fourier transform, doing it by hand as a way to learn a programming language. And I kind of like that, and I do that today whenever I learn a new programming language, see if I can write a fast Fourier transform. Not using any of the libraries or anything, because there's numpy.fft, and you can do fast Fourier transform there. But if you can write out a fast Fourier transform yourself, you not only learn what's going on, but you can also learn the programming language pretty well. It's a fairly intricate algorithm to write, but it's not overly complex, and it's a standard result that every programming language will have kind of a module for it, so you can check it against. That's why you guys have that assignment. So you don't have to implement the whole thing, you just have to implement bits of it. And it should be fairly easy. If you are still just learning Python, it should be kind of easy enough. And if you know Python, it should be very easy. Let me know. Anyways, this whole thing. Yeah, so instead of doing this discrete Fourier transform, which is computationally expensive, the idea is instead is that you take these continuous signals, samples, and lay them out onto a grid. And once you're on a grid, the regular nature of the data allows you to do a Fourier transform in the fast way. And when we make an image in interferometry, it's typical to make a 1024 by 1024 pixel image, maybe a 2K by 2K, 16K by 16K. I mean, these are very big. So if you 1024 squared, whatever that is, a million pixels. If you're doing an n squared operation on a million pixels, right, it's a really big operation to do. If your image is only 16 pixels by 16 pixels, discrete Fourier transform, perfectly reasonable thing to do. It's not that many more operations. But when we're doing kind of real interferometry, where you have these big fields of view and you have a high resolution, you really need to speed it up in any way you can. Okay, show some. Okay, so this is kind of returning. You guys have hopefully saw in the visibility lecture, the UV coverage, right? This idea of UV coverage from positions. So this is a bit of a rehash, hopefully. Is that, this is a typical layout of the VLA. There's 27 elements, all spread out. This is the A configuration. I think the A is the most compact. So the VLA, you can move the dishes right on these tracks, these 3 tracks. And this is the most compact version. And so you can see it's something like the baselines are maybe a kilometer by a kilometer at most. That's a fairly compact array. Something like Meerkat, the core, is about a kilometer wide. And I think about half the dishes are within that core, and then the other ones are out to about 8 kilometers. Okay, and then, so when you do based on that antenna positions, you can compute your UV coverage. This all looks familiar, right? No? Or you guys happy with this? Yeah. So you have some kind of interesting UV coverage that's typical of the VLA. Just kind of star pattern that shows up and that you can typically see. And so that's just for a snapshot. For kind of a longer integration, you have a new sampling. So this is looking right at the North Pole. Well, for the VLA, it's the North Pole. If it's for Meerkat, you do South Pole. Over 6 hours, you see that this UV coverage is filled in a lot of the UV space. Okay. So this is hopefully reminding you on Tuesday about the various sampling functions that Trinko talked about. This is basically one of these disk sampling functions, right? This disk is filled in, or most of this kind of inner core has been filled in by a disk. The Fourier transform of the disk. Who knows the Fourier transform of the disk? Everyone knows what this is. I'm just scared to say it. Fourier transform of a disk. Come on. Circle. Well, Fourier transform of a circle. What's the Fourier transform of a circle? An aperture. An unblocked aperture. Is an area function, right? You guys have heard that term? The sinc function. A 2D sinc function, right? Is an area function. Yeah. That's a really good one to remember. Because chances are, if anyone asks you what's the Fourier transform of this, it's probably a sinc function. It's almost always the case. It's a 2D sinc function, 1D sinc function, maybe a 3D sinc function. You call it area disk or a sinc function. There. So you can imagine as you fill in this, that the longer you integrate, or the longer you observe, kind of the UV space is being filled in. Now, it's not a perfect area function, of course, because you don't see it, but there's these gaps here within the disk. It's just kind of limited the resolution of the image. And then you have these tracks, these outer tracks, that kind of add a little disform to the Fourier transform. So you can think of this as some area function, but remember, the farther out you are in the UV space, kind of more resolution, more to the higher frequency spatial resolution you're sampling. So these outer tracks here are really sampling those higher frequency components. So giving you a bit more resolution, but they don't fully fill in that UV space, and so it's not as nice as this inner core. And so one thing you can see is this is the same amount of integration time, but in this case I've changed from looking at 90 degrees declination to 45 degrees declination. And you see that instead of this nice kind of disk that's sampling you start to get this figure 8 pattern that's being filled in. And that's going to lead to and this figure 8 pattern with these little wings and maybe even like a clover leaf envelope one. But maybe you can even start to get some intuition for what this UV pattern will mean. Is that you can see going north-south, it's better sampled and kind of out to longer frequencies, but east-west is a little more narrow. So that means your PSF will look a little funnier. It'll look kind of narrow north-south, but it'll be a little fatter, right? It'll be kind of like a squash ball. Because you're sampling more of the high frequency modes this way versus that way. Yeah? And you can kind of start to imagine what this PSF should look like. And it gets kind of even worse as you go down to lower declinations. This is 20 degrees declination. And so you're really not sampling these east-west modes. And so now your nice, perfect PSF is getting squashed and squashed and squashed. And when you get to 0 declination, you're having a real bad time. I think this next one will be 0. So with the 0 declination, instead of having these arcs, you only have these single lines, right? Because what's going on is that you're looking at the kind of plane on which the Earth rotates on. And so that means there's no arc to it, right? It's just a straight line. And so you actually get a really bad sampling looking at declination 0. So you often find in surveys or observations people avoid these low declinations. It's not because there's no science there. It's just your imaging won't turn out as well. Sorry. Okay. I'm going to talk about gridding. Gridding is not so important for you to know about in the sense of you will hopefully never have to implement a gridder. It's a very computationally, you have to know quite a bit about computer science to do it well, and most people just let someone with a good computer science background implement it. But it's really good to know in terms of what it's actually doing in interferometry and the effects it can have. So you have these UV tracks that are cutting through. So we'll look back at one of these. So you have this track that's just cutting through, right? And if you imagine if you chop up this image into a big grid, you see that as the tracks go by, they'll be in certain grids, and sometimes they'll be between grids, or and they'll go at different speeds, right? Because over 6 hours, it'll spend most of its time here, and then it'll shoot real quick, and it'll slow down again. Because remember, it's going through some volume. And so the projection of that UV-W space into U and V means that you projected the track moving in some volume down to a 2D fix. And so kind of I guess it'd be, you could think of it as having some velocity perhaps. I guess it'd be you're throwing away one component of its velocity. And so even though they're at constant velocity within volume, they're non-constant projected velocity of the UV tracks. So all this adds to that the UV samples, if this is our UV space, this grid, it's not as if every single UV sample perfectly hits each point, right? And in fact, most of the time, the points are never touched, or never sampled. And sometimes you might, for a given grid, you might sample it a few times at different times with different baselines, or you might sit in that grid longer than a nearby grid. So you have this whole issue about you're not sampling the UV space on a grid, and we really want to sample on a grid because that makes everything in our life easier. So we need to do this thing where we basically take our irregular sample data and put it onto a grid. Here, kind of more of we can imagine this as like instead of a 2D space, we can do a 1D space. Is say these blue points up here are our various UV samples. And the amplitude varies a bit because of just system noise and whatnot. But you can see, if you project it down to this line at the bottom, the green points, is that you can imagine this as a 1D grid, is that some points have, this one on the far corner has 4 points, maybe there's one right on the edge, and then there's nothing. Next one has maybe 5 points. This one has 1 point. And each grid point has a different number of UV samples. But that's okay. That's just the way it is. We'll talk about in a minute about how we deal with that. But the real question right now is, what does it mean if you have a point, if you distribute a point here? So let's say this one between 5 and 10, you see that there's 2 points there, 2 green points. One right on the edge and one kind of in the middle. So do you just add those two together and say they're the same? Or do you say, well, the one in the middle is right in the middle, so that means that's a good point. The one on the edge, well, the one on the edge both represents kind of the point within that grid and also next to it, right? There's some kind of, you wouldn't want to say just because it's on the edge, it's slightly in one grid versus the other, that all the power must go in there. You kind of want to say, well, let's give half and half of the power. Let's distribute it in some function. And so, kind of the typical thing you do is you convolve your sampling. So, here. So we eventually want to get to some gridded visibility. We have some sampling based on our array configuration. So this is what depends on the frequency, depends on the declination, depends on the array layout. This is our, sampling function we were talking about in this sampling function. This would be a sampling function, so it's a function of the array. And then we have this thing called the gradient convolution kernel. And that's this red thing here. What's that? Sinc. And what's the Fourier transform of sinc? 2D version, yeah, but it's a 1D version, Fourier transform of the 1D sinc. Vox. Yeah, there you go. Remember this. They come up everywhere. So what's going on? So this is your grading kernel. So it's just some function. And then this last thing is what's called a Shaw operator. These two kind of make up the whole grading operation. And so what's happening here is this is what we measure. This is what we know from our sampling, from our array configuration. So these multiply together gives you kind of your visibility distribution. And you want to convolve that with this grading kernel, which is typically the same function. And then what this Shaw function does is it's kind of, I don't know what the right term for it would be. The 3 lines basically are kind of a pictogram almost, right? Of the gridding operation.
want to raise his
Okay, so there's anytime, say, you have some function, and then this is, and say you want to decimate it down, you just want to sample it every once in a while, so in some regular pattern. So you want to sample something like this. You just basically want to measure the point here, point here. So if you're decimating down a signal, you just want to pick these points here, and this is some regular pattern, right, on some continuous function. And so you can see what the Shaw function does is it describes this sampling, how kind of spacing between, and kind of the pictogram of the 3 is basically kind of indicating the regular sampling of it. So you have some, so you convolve, what you do is you convolve your continuous visibility function with sync function to distribute that power out in some way that makes sense, and then you need this gridding operator to then sample it at a regular interval. So what's computationally expensive here? It's this convolution, is that you can't do the convolution trick of taking the Fourier transform of it and just multiplying them together, because you're trying to do a Fourier transform of it, right? You're trying to do, because you don't have regularly sampled data, you can't just Fourier transform of it multiplied by the convolutional kernel and then transform it back. You have to actually do this kind of slow convolution way. That's why it's tricky. But it's better than doing the discrete Fourier transform. Okay, and then kind of the opposite is this idea of degridding. Is that given that you have some gridded visibilities, you have to deconvolve it. And it turns out you use the same Shaw function, or the same, not Shaw function, the same sync function to deconvolve it. And then you have your array sampling function. So they look functionally equivalent to equations, but if you actually sit down and try to implement it, they're very different. And there's all sorts of efficiencies that are done. One question you might ask is, why would you ever want to degrid? Why would you ever want to go from this max regularly sampled data to some continuous function? In deconvolution, it turns out to be a really useful thing to do, to improve your image quality as you loop through. We'll talk a bit about that in the deconvolution lecture. How do you guys feel about gridding or degridding? Any questions about that? Okay. You don't, it's really useful to know how it's done, but you don't ever have to do it yourself. But know that's always happening, and that someone implements it. And oftentimes what you'll see is, say you have some measurement sets, you want to produce an image, and you produce an image through like CASA Imager or some other imager like WS Clean, and you give it all the same parameters to a bunch of imagers, you often see different results. And chances are it's because of how gridding was implemented. So there's slight variations due to the implementation. It turns out you can do, so the simplest form going back to here is, for the gridding kernel, is that you can use a sync function, but you can come up with other stuff. Yeah.
That was my question.
Yeah.
Using the sync function as a point spread function, basically.
Yeah, so
it will be other functions depending on your configuration of the telescope.
Well, not so much the telescope. It's more about how you. It's all about how you decide to implement this gridder. It turns out the sync function is a good one to implement because there's a lot of fast math libraries that can do it. But oftentimes someone might use something like a prolate spheroid, which is just so the problem with the sync function is that it's infinite, right? So the Fourier transform of an infinite sync function is a nice box, and that's ideal. This area is. Our sink is like this. And our Fourier transform of that is a box, right? If this goes out to infinity. But you obviously don't go out to infinity, you clip it. In fact, most implementations chop it off at some point and say they call it support, how big your support is. And so you only do this. And in that case, instead of a really nice box, you get something box-like with weird side lobes. So it's still quite box-like, but it's not great. But you can use things like, there's these things called prolate spheroids, which are nice in that they're basically just an ellipse, and they have a nice cutoff point. And the Fourier transform of this is pretty good too. Fourier transform of this is actually it's pretty much like that. There's a little bit of bump to it. This is actually a better function to use if you can, but computationally it's much more difficult to compute this than this. This is kind of it's an efficiency trade-off, basically. It's how you want to grade your data.
So,
Yeah.
what are the effects of those side lobes on the issue?
So, right, that's exactly, I have a slide or two about this. So I do have a slide or two about the aliasing effects. But basically, remember this is you have some grid that you're imaging onto. And say in the perfect world you have a point source here, and a point source here, if that's our simple image. But if we apply this gridding kernel, which has these side lobes, what will happen is that there'll be a little power showing up in each one of these, because some of the power from the source that's here is will show up in the nearby side lobes. And so you always have a little bit of power spreading out. And now the difference between this and this first side lobe is massive. You'll never see it. It's below the noise. But if it's quite high, you'll get aliasing effects, which is actually it's right here about it. I'm going to jump back to that slide in a minute. So this is the effect, is it's all right, is that if you have a really stupid kernel, so one thing you could imagine doing is that instead of having a convolutional kernel that's a sinc function, you can do this, the stupidest way to grid you can think of is, instead of spreading that power out, is to say, well, I have this signal, I want to image this. Go back to here. For example, here, instead of applying this convolutional kernel, what you can do is you can just put it in the closest grid. So there happen to be 4 points here, just add all 4 of those points, and put them in that grid point, and do the same for all of them. And so that's equivalent to applying a convolutional kernel that's boxcar, right? So wherever, if the point is in here, it's given a value of 1. If it's not within this region, it's given 0. It's simple. And of course, Fourier transform of that is our sinc function, right? Now these side lobes are quite significant, right? First side lobe of the sinc functions, 15, 20% of the first one. So you're definitely going to see power spreading out. If you're going to ever implement a gridder, this is a good thing it's a good idea just to do that, just to make sure all the other mechanics work. But you're going to see these, what I call aliasing effects. So if you have a point source there and you use a boxcar convolution function, you'll see basically power showing up at all points away from it, right? And so the trick is to fix this, you have this anti-aliasing filter. So actually, this is a point of 9 points, but all these points on the edge are artifacts. And so if you apply a proper convolutional kernel, then you don't have this aliasing effects. I mean, they're still there because the side lobes are still there, but they're somewhere below in a way, so you'll never see them. Up here, basically that's the comparison. Given a boxcar kind of convolutional function, you can see these side lobes is in decibels, so log units. But if you a Gaussian is also a nice solution. Very nice side load. The sinc function is computationally very cheap to do, and it produces, it still has this low level. It only goes down to kind of minus 10 dB, whereas the Gaussian function is a really sharp function. It's computationally difficult to compute the Gaussian function. It's all some sort of engineering balance. There's oftentimes perfect solutions that are just computationally not efficient to do. And so it's much better to try and do, well, what can I do that's approximately correct that's going to happen? It's going to give me an image faster. Or just any sort of programming task, right? Is that the best solution is usually some approximation to the absolute solution. Okay, oh wait, skip past, I need to move this. This is a really useful slide to have. And in fact, at the end of the last slide on homework, it's just basically using these simple equations to answer some questions. Hopefully the homework for today is very easy. You need to know when you're making an image, you need to decide what resolution you need and how big the image should be, right? This is a common thing to do. If you are imaging with a VLA with 20 kilometer baselines and the beam size is half a degree, that's a different kind of resolution and image size versus something like Cat7, which has a few 100-meter baseline and a few degrees beam, right? So in order to figure this out, you can use just these simple equations. So if you have some known resolution, and your resolution is basically your maximum baseline, for example. Let's just take that, and it's wavelength dependent and dependent on the array configuration. And then you have some field of view, which has to do with the size of the antenna, right? So for Meerkat, Cat7, it's something like a degree or two field of view, typically. And so it's pretty easy to work out the number of pixels you need. So a really important point, I should write this down and write it down many times for you to see. If you're making an image, because the Fourier transform really works well when it's 2 to the power of n, you should always make images of that size, because they'll be much faster. So an image so you really want like a typical image of 1024 is really good. 1024 is what, 2 to the 10? Something like that? That's good. You're going to make a faster image if you say 1024 by 1024 than if you say something like 980 by 980. And you'd say, well, there's fewer pixels here versus here, but because this is 2 to the n, the FFT works much faster. So what has to happen here, and maybe you'll see this in your homework, is that you'll do as many fast Fourier transforms you can do using this, but at a certain point you're going to end up with an odd number. And then you have to do a really slow normal Fourier transform. So anytime you make an image, say you work out these resolutions, or the number of pixels, and it's something like 6,700 pixels by 6,700 pixels. It's probably faster to do an 8192. Is that right? That size image by 8192 image, even though it's more pixels. You'll notice it. I guarantee it. So for the resolution, you can figure out kind of the size of the grids. Basically by taking the number of pixels and the resolution you have. This will give you kind of the grid size. Because they should be kind of the inverse of each other. Another point I wanted to make. Anyways, okay. So 2 to the power n image, very good idea. So what does resolution mean here? So if you use the angular resolution equation, what is it? What is it? Delta 3 equals 1.22 right? That's your angular resolution. And so typically, you can kind of, as long as you define it, it's fine. These resolutions, when you compute it out this way, gives you usually fairly small image sizes compared to what people typically do. So what is typical when you make an image is that you oversample this by a factor of 5. Just a rule of thumb people do. So instead of, if this number comes out, the number of pixels you find to be is 100, usually people make a 512 by 512, which is a factor of 5 higher. The idea here is that this resolution kind of is the size of your PSF. Basically, it's something like this size. So each pixel would represent this. But in fact, what you'd rather do is you'd want to kind of sample this PSF a few times. Just to over-resolve it. It tends to produce kind of nicer images, but this is just a rule of thumb. And complete information is here, but a nicer image is to oversample. So keep that in mind when you make images. Okay, so let's talk about, have you guys talked about dirty images? Or do you guys know, have you heard the term dirty image? You? Okay. I'm trying to remember what the other lectures, I'm sorry, I missed the other lectures. The dirty image is simply the visibility, the sample visibility gridded and Fourier transformed. So it's what it is the image, it's your original image involved with the PSF, which remember is Fourier transform of your sampling function. And then this is your gritter in here. So yeah, your PSF multiplied by your, it's involved with your PSF. This notation needs to be slightly, it should be a parentheses here, because it's a convolution of these two. Anyways, so it's fundamentally, it's your visibility sampling, your visibilities, which are gridded, and then you have you compute your PSF, which is your sampling function, and you convolve them together. And so, given this our original image, our favorite duck, we reproduce this idea of a dirty image, which should look quite similar to the images you saw on Tuesday, right? Some sort of sampling function, and you can tell from here is that this PSF that's convolved is a pretty small PSF in the sense that it's it's not a small PSF, it's a pretty big one, because a lot of the detail is missing, right? This is a pretty significant low-pass filter. So all the high-resolution detail, all the high spatial features have been filtered out, and all you see left is just kind of this broad structure, the wing and the head. And in fact, you don't see that in kind of the zero spacing either, because, well, interferometers don't sample that zero spacing. And so then you get some kind of, this has, if you were to compute the mean of this image, it'll be a positive number, right? When you take an image of, so this would be what's called in kind of computer science term a natural image. Natural images always have positive values. Now in interferometry, we produce images which have negative values. And that's because when you take this photo, each pixel has some power, right? Because it represents some number of photons coming in. So there's no notion of a number of a pixel having a negative value, right? So if you compute the mean of this, it's going to be some positive value. But in interferometers, there's no baseline. The shortest baseline you can ever have is when the two dishes are touching, right? You can never have them overlapping. And that overlapping mode is the zero baseline spacing. And that represents the lowest spatial mode you can have, which is the same as the mean, the average of this. And so anytime you make an interferometric image and you compute the average, it should be zero. Unless in very special cases, but because you don't measure that zero spacing. And so then you see this image that's both positive and negative versus the real image. And this is a big problem if you ever want, if you're doing interferometry, if you want the absolute value of some source, you can't just look at it with an interferometer because you won't ever get the absolute value. Because the absolute value of a source is the mean value of that source, right? Plus whatever noise. So what that means is you can use a single dish. A single dish will measure that zero spacing because, if you think of the dish, that has high frequency modes down to the middle of the dish, which is the lowest frequency mode. So it's measuring all those modes. So in fact, you can combine single dish observations with interferometric observations to measure the absolute power. If you want to kind of absolute flux calibrate an interferometric image, you have to do something like looking at a flux calibrator source and figuring out what the flux correction should be. And then you can apply it. So it depends on if you care about the relative flux within an image or the absolute flux. So there's different tricks. Okay. So the dirty image, we're just going to simplify this. I mean, let's ignore the gridding. I mean, gridding was kind of there as kind of a hint of what's going on. But for the most part, people ignore the gridding and say, well, sample visibilities are sampling function times some observed visibilities. And there's some process that takes it and puts it onto a regular grid. And our dirty image is simply the Fourier transform of those functions. The sample visibility function, which is just, you see it's the Fourier transform of sampling times observed. And so you can see the dirty image is FFT of the Fourier transform of the sampling function, which is the PSF, times this Fourier transform of this IV observed, which is simply, you can think of this as like the ideal sky, some truth, some real sky. There's some real sky that we don't actually ever have, or we don't actually ever see because, well, we have some sampling function that hides it. Even though mathematically we see it's there, it's kind of a mathematical construct in reality. We can never get to this. Now the process of trying to get to here from this is deconvolution. And we'll talk about that next week. And that's kind of an imprecise part that takes a little kind of bit of learning to figure out how to do. But because it's important to remember that your sampling function is that you have the UV space, UVW space is infinite, right? And it's continuous. Your sampling function is neither infinite nor continuous. And so you're inherently throwing away information, right? There's just no way to reconstruct something once you've thrown away information. You can't perfectly reconstruct it. You can almost kind of approximately reconstruct it based on kind of some ideas you have about what it should be. And that's why the convolution is a little tricky. Okay, so this all right? Some logs here. So I think going back to this duck, what is the PSF that produces this? And in this example, I just use the Cat7 sampling function. And what's going on here? This is the U and V space, and you can see kind of at the core, there's a bit of color, and then it gets a little light blue, so it's some value, and then it becomes just blue and means 0, right? So what you have here is that these lower UV spatial modes, these lower spatial frequencies are sampled. Not just sampled once, but many times. It turns out, each one of the pixels in the middle is sampled hundreds of times, whereas pixels out here, UV coverage out here is sampled never. So we have this issue of where we're kind of oversampling stuff, undersampling stuff. Undersampling is kind of fine. You can go, well, I just don't know that back to the spatial frequency, so there's 0. The problem is that, well, what happens if you have a grid? It's easy, when you think about gridding, each grid might have a few pixels, and maybe some have 1, maybe some have 10, maybe some have 100. That means that for a grid sample of 1, you're just sampling that, you're just adding 1 sample. But for the grid where you have 10 points, that means you've sampled that grid point 10 times. So then you'd want to say, well, I know the value of that grid point 10 times better than when I only sample it once, right? Statistically, add more information. about what the actual value of that grid is versus the undersampled one. And the question is, well, what does that mean? What effect does that have? And so we'll talk about weighting functions in a minute, but it's useful to kind of consider this. Consider what's going on here is that if we were to take a slice of this image, so let's just do a cut through this image. And you can kind of, if we were to first approximation do that, there's no points in the middle, right? And then because of that zero spacing, then you have this, and it shoots up on either side. And I mean, to first guess, it's something like that. Something like the amplitude, based on the color of these values, it drops off like this. And so the points, so this is 0, and our UVW, or UV spacing is 0 here. That means this gap is missing, but then the points really near 0 are really highly sampled versus points further out. And so what this is going to produce is, if you do the Fourier transform of this, is some weird triangle-like function, right? Because you're saying, I value the spatial frequencies, these lower modes, more than the ones out here. Versus, well, what you could do instead is say, instead of giving these all 1, or giving these some high value of, say, 100, what you could do is you could do a different function where you say, well, anything that's within, any grid point that's sampled, let's just give it the same value. You can do kind of just create a box. Still have this gap issue. But in that case, you'd say, well, any grid point that's sampled is statistically equivalent to any other point. And so what you can see is that this Fourier transform of this triangle function, let's kind of just assume it is a triangle function, says give more value to these lower spatial frequencies. So that means it says give more value to the kind of the large scale structure, versus this sampling function says, well, distribute it equally. And so I'll show you in a minute. Basically, this form of weighting basically says give me more resolution, but at the cost of sensitivity. Whereas this function gives me less resolution, but more sensitivity. These are kind of two trade-offs you can do. Okay. Okay, now that you guys have stewed a bit on what I talked about, is there any questions before I start again? So all this coming back to how do we make an image from our visibility samples, right? We have this interferometric array that we're measuring baselines, where the baselines are measuring some kind of phase differential, different spatial modes. We made all these measurements. We do this because then we get all this resolution, but we're missing gaps, right? We don't measure every aspect of it. We measure kind of enough. And the problem with these arrays is that we oftentimes, we necessarily measure the lower spatial modes versus the higher spatial modes more often, right? Because any array configuration you can imagine is always going to be more shorter baselines and longer baselines. And so what we need to be able to do is we've produced this array that does this really weird irregular sampling, and we want to produce an image out of it. So we talked about gridding, how that works to kind of regularize the whole thing. But the question is now that what happens when you actually grid these points? So what happens when there's more, for a particular UV grid, there's more samples in one versus the other? How do you treat that? And this is this idea of what's called a weighting function. A weighting function is kind of like a bit of an abstract notion, It's kind of, like the Drake equation. The Drake equation breaks down kind of the number of intelligent life in the universe or the galaxy. And there's all these components about like the number of stars in the galaxy, the number of stars with planets, the number of planets which are kind of have liquid water, and the fraction of life on that comes from liquid water, and dot, dot, dot. It's more of an abstract concept. It's not really an equation that you actually implement. It's just kind of a way of breaking it up into components. And it's the same with the weighting function. So far we've just been talking about the PSF, it's the Fourier transform of the sampling function, this geometrical sampling function. In reality, I've been lying to you. It's really more kind of general in this idea of a weighting function. And one of those components is this array sampling function. And probably is kind of the most important one. So then there's this some sense of this, there's this another component called the reliability. Say you have an array of dishes, and say one of the dishes is bad or it's not as sensitive as the others. You would want to give every baseline measurement with that dish as a part of the pair kind of less weight rather than some of the other baselines. So say you have some collection of dishes like in VLBI where it's kind of they're spread throughout the world, and they're all different dishes made by different people. They're going to have different sensitivities, Part of, in VLBI, you might have Arecibo, the 350-meter dish, with a 20-meter dish, like a Hartrau or what, So obviously you want to weight them differently because some are more sensitive than others. So that's this idea of this reliability. There's this idea of a taper function. I'll talk a bit about this later on. Is that if you have some array, and you have some source you're looking at and you want to image it, and you know something about the size of that source, and it's a weak source, you can apply a tapering function, which is basically applying this idea of a match filter, which maximizes the signal to noise of something of the size of the source you're interested in at the cost of other things. And so sometimes if you're doing something on a weak source, you might apply a tapering function. This last one, this density function, is quite often what we think of when we think of weighting. And there's this, kind of going back to this example, this is different types of density functions. How do you weight the density of the UV sampling? And so there's two kind of cases there's two specific cases and kind of a more general case with the density function. So the density function, what we call, there's two that will often show up is, you'll see when you make an image, it's called natural or uniform weighting. And so natural weighting is kind of in the name, it says, well, naturally I will weight everything based on what its value is, in the sense of, if I observe a UV grid point 100 times, it should be 100 times more valuable than a grid point I only value once. So that's this triangle function. This is what's called the natural weighting. The natural weighting, it basically says, the number of samples per grid is the weight that's given. And then you have this uniform, which is kind of this flat bit. And that just says, just give everything a uniform weight. It says it doesn't matter that statistically I've measured this point more often than this point. I've measured it once, and I'll assume they're all equal statistically. These are two kind of extremes, and they produce very different effects. So let's take a very simple sky model for Cat 7. Say we have a sky filled with a bunch of sources, kind of Gaussian sources, right? They're just basically stars or galaxies, whatever, different intensities. Now, if you were to use something like Cat 7 and do different weighting functions, you produce different PSFs. Just remember that the PSF is a function of the Fourier transform of a component that includes a density function. So for natural weighting, you produce this type of PSF versus uniform. They're on the same scale. And so what you can see is that with this natural weighting, the kind of inner lobe is bigger, right? It's a little fatter than the uniform. So what that means is you have lower resolution. And that should hopefully make sense, is that because you're weighting these modes more than these modes, that means you're weighting at the lower frequency, or the lower resolution modes versus the higher resolution modes. And so this is kind of a ratio here. That's kind of, can be thought of as a ratio here. You can see, oh yeah, my resolution's lower than the uniform, where I'm kind of favoring the high resolution components just as much as the low resolution. And so you can see with the uniform weighting, that central lobe is a little tighter. But what you can also see is there's kind of a bit more of this kind of some sort of structure here. And actually, it's quite negative. These what you call negative side lobes in the PSF. Versus the natural doesn't have these negative side lobes. There's a little bit of negative stuff, but not really. It's a little smoother and whatnot. So what this kind of effect it creates is that when you use a uniform weighting and you make an image, what you'll often see around a source is a negative bowl, versus the natural weighting is kind of a smooth taper. And these are, of course, not real effects of the sky. It's the fact that you're not fully sampling the UV space. And so if you make an image using those PSFs, you can, of that same sky, you can see some interesting stuff here, right? Is that the natural weighting technically is more sensitive, but because of your lower resolution, you kind of blur out some of this stuff. Or, yeah, lower resolution blurs out. So even though you know there's some sources here, they're harder to see versus this uniform weighting where you can kind of, you know that there's sources here. You go back up to this. There's kind of these sources down here. Let's look here. You can kind of make them out that they're there, but here they're basically blurred out. It's very noise. So uniform weighting is really good for point sources. They basically, it says, if I have a point source which is unresolved, you want to value the high resolution as much as the low resolution, and basically push as much power into the PSF as possible. Let's say you have some big blobby extended source. If you do uniform, because the blobby source has these low resolution components, and if you do uniform on it, what you'll see is you'll see it washed out and disappear. And so in fact, if you have a resolved source, you tend to want to do natural weighting versus uniform. And then you can kind of generalize this a bit more, is what's called robust or Briggs weighting, is that these are the uniform and natural are kind of at two ends of the spectrum. And you can imagine weighting them kind of in some ratio. And this is this idea of robust weighting. And so in red so this is a cut of that PSF. We go back to, so if you imagine you just cut the PSF here, and we go plot. So in the natural weighting, see this red, the bowl isn't as significant, it's kind of a bit more flat. And so you'd say the first negative side lobes are low, and then you talk about this bump as your first side lobe of the PSF, and that's also low, so it's a nice kind of taper, whereas the uniform is quite wobbly. But you can imagine adjusting kind of the ratio between them, and then there's basically these values here are the parameter of the robust weighting is that you can vary it accordingly. And so it's actually quite typical to use the robust weighting. And what you tend to pick is, I think a typical one is people go for like -1 usually. You tend to prefer a uniform because most of the time when you make an image of the sky, this is again, it depends on the science you're doing. When you're making an image of the sky, there's going to be a bunch of point sources almost all the time, right? There's a bunch of galaxies everywhere, and you'll be sensitive to them. Maybe that's not what you're interested in. Maybe there's some big blobby source you're interested in, but there's still always going to be stars there. And so you want to kind of resolve them and figure out where they are. But if you're interested in this blobby source, you don't want to go straight uniform weighting because they'll wash it out. And so some kind of ratio between the two and using this robust weighting is a very nice thing. Have you guys done imaging yet? Have you guys made images yet?
No, that's only
So I mean, it'll be typical in almost every imager you'll see the weighting scheme. It's usually called weighting, but really it's a density function. And you'll see natural, uniform, robust, or they're called Briggs sometimes. There's a few others. There's something called radial, which will show up sometimes. I think what else? This was it super uniform. There's a super uniform weighting. It has to do with grading. But the typical ones are uniform, natural, and robust. They have their different uses. Any questions on that? Let's see. Let's see what we make images. Taper functions aren't used a whole lot, and they're used mainly when you're interested, when you made an observation of a source you know something about, and you want to maximize its signal to noise. Say it's a weak source, and you only have some limited observing time. What you can say is, well, I know what the source kind of looks like, and so I can kind of use that knowledge to improve the signal to noise. This is what's called the taper function. In signal processing, there's this idea of a matched filter. Is that if you have some signal, you know about, you want to discover in a noisy system, say you have some, let's use our, this is what's called a chirp function. So if you ever do pulsar studies, pulsars produce chirps. It's useful to know. So you have some chirp function, and then you have some system that's really noisy. And if you add them together, then I'm not going to try to draw them. Maybe I'll try for a minute. It'll be a little shooting up and whatever. That's something like that. Goes to that, right? You add these together. So there might be signal in here, and we know there is. We've added it in. But the question is, how do you maximize? If you have this signal and you know something about the true signal, how do you get the maximal signal out of here? So it turns out if the solution here is you have some function, and you actually then you do basically you call it autocorrelation, or in signal processing you apply a match filter. And the idea is that by multiplying this, by convolving this with this, you'll recover the original signal. It's kind of roundabout to think about, because oftentimes we're looking for signals we don't know what they look like. And then in that case, you don't use a match filter. And another thing, like if we're observing a source, chances are the only reason you observe a source is because you don't know anything about it, or you don't know full information about it, because otherwise why would you observe it? But if you have some partial information, you can do something like, well, I know approximately what the source looks like, and so I'll apply that, so I'll try to match that filter with the sky signal I have and to maximize it. So the idea here is that applying a match filter maximizes the signal to noise of your signal. It's quite common to do, and it shows up all the time. It's often called that. So say you have a typical radio source is like a Gaussian, right? Is some galaxy, some globular cluster, some anything is usually pretty Gaussian-like. And so a typical function you would want to apply would be a Gaussian. And so these are Gaussians of different scales, and we'll treat them like our tapering function. So say we have some true signal. This is our very simple sky. We have some kind of oblong source, some galaxy, and we would like to maximize the signal to noise of that. So say we have in some noisy signal. We can see how there's a bit of a bump there, right? But it's not. It's kind of hidden. But if you know what the source should look like, when you cross-correlate them together, you produce this filter signal, where it's clearly there's a source here, and everything else, all this noise is washed out, right? And we've successfully gone from a state where the source is buried in the noise to a state where there's a high signal. And say we apply an unmatched filter, smaller Gaussian, the signal's still there, but it's not as strong, right? Versus here, which is quite obvious. The noise is quite high here versus here where it's much lower, because we've matched the filter.
this idea. And so the kind of the typical thing is that you almost always have a bunch of sources in the field of view you're observing. They have different scales. So, there's this light diffuse region, there's a source, it's a kind of a strong galaxy here. And if you make it noisy, you can see, well, you probably pick out that small compact point source. You might have a guess about that kind of larger source, but you definitely don't see this source at all, right? Like, it'd be hard pressed to say. But if you know kind of these different size scales, we can kind of accentuate different signals. So by applying the different size match filters, this one pops out now when we use the right size filter. Here, even though we don't use the fully matched filter, it's still starting to get good, right? So you can start to guess, but maybe you don't. Maybe you're not convinced, but this one you're convinced about. And when you use that match filter, you might begin to guess, but not really. You definitely know that's a source. And so if you're just observing the sky and you're kind of looking for new interesting things, you don't apply a taper function, right? Because unless you have some intuition about what you're looking for. But say you're observing some well-known source that's some extended lobby thing, well, you might want to apply your function, your match filter, based on the knowledge you have of it to emphasize that SNR. And then, okay, here's that same sky again, but if we look at it, applying different scale match filters, and these all being point sources, you can see the smaller match filters, the compact ones, which are kind of more attuned to point sources, make the sources pop out. But these larger taper functions kind of blur everything out and leave kind of a few sources behind. A match filter is pretty good for, if you use a large match filter, kind of a large Gaussian, it'll blur out a lot of point sources and leave behind the large scale structure. You can think of this as, going back to the fact that it's a weighting function, is that, we have this sampling here. Again, we have the sampling based on the geometry. And then a match filter basically is, if it's a Gaussian, if it's a really small Gaussian, that means it's going to be sensitive to large scale structure. And so it'd be a Gaussian like this that you'd apply on top of it. So you're basically saying, give everything here more weight, these kind of low resolution modes more weight, whereas throw out these high resolution modes. And Gaussian is the most simple type of taper function you can come up with. I guess a boxcar would be even simpler, but you can come up with any function you want as your taper function. It just depends on what you know about your source and what you'd like to get out of it. Okay. So all this up until now has been more of how do we go from this UV sampling to the image domain. This is all very classical imaging techniques. You have your imager, you apply your weighting functions, you have your gritter, all that stuff. All this stuff is kind of incorrect. Did Etienne cover consider?
Yeah, he did consider, but not the W term.
Okay, right. So maybe you remember from visibilities, maybe you block that out of your mind already, is that that we've been, throughout this whole thing, we've been using this relationship that the visibility space is equivalent to the Fourier transform of the image space and in reverse. That's this relationship, this linear relationship between the two. And then we use this equation up here that kind of has this image term and the space term that gives us our visibility, and it's integral over all the space. But maybe you remember that this is incorrect, right? This isn't true. It's approximately correct for certain situations. And we use it because Fourier transforms are very nice, very mathematically pleasing. In fact, the true kind of relationship is this Mann-Sidder-Zernike relationship, which has to do with UVW and the Ln and N space, these kind of volumes relationships. The problem with using this is this is not a Fourier transform. It's not 3D Fourier transform. It's just it's an ugly function. But what we do is we made the approximation that what we call this W term this term here, we set that to 0 usually, or set some constant. It doesn't actually matter what that value is, we just make it constant. And what that does is it takes our 3D UVW space and projects it onto a 2D plane. And when we're on a 2D plane, we're good. We can do our Fourier stuff and make our images. Now, why are we allowed to do that? So in classical interferometry, you make two assumptions. First, you're making narrow band images, so kind of a small amount of bandwidth compared to where you're observing. And the other thing is that you image only a pretty small field of view. And it turns out it's a small angle approximation. And so both those assumptions allow you to basically set this to a constant and reduce it down. In fact, in modern interferometry, we have pretty significant bandwidths, and we also want to image more and more of the sky. The sky turns out to be round, right? It's not flat. And so because it's not flat, we have to start to consider what this W term means. Historically, why you do this, why you use this kind of approximation, is that it's computationally easy. But now we have computers that actually can do computationally hard problems, and so why not make better images, more accurate images by including this W term. And so there's kind of a number of ways to do this. It's again, just like gridding, it's useful to know this stuff. But unless you're writing an imager yourself, you're really not going to use it. But most imagers have these features built in. And so it's kind of, and some of them just built in by default that you just use. You don't have to worry about computationally what's more important, what's better. Okay, so these are this assumption we make, this small angle approximation, is that we say, remember this L&M space that Trenko talked about a few lectures ago, kind of has some extent, but if we say L and M are quite small, we can say, well, there's this N component is there, but since if L and M is small, we can ignore the N, set it to 0, and then we can use this relationship to say, well, this is approximately 1, which makes this 1, and so we're good. So that's how we get to our next bit. And then we can approximate consider as this. And this gets us back to basically our Fourier transform. And so then we have this idea of this delay term, this W term, which, so if this is 1, and we can separate this out, right, this E to the UV and then E to the WN, that's 2 terms. And we call that the W term. And you can say that's a constant value to get our relationship here by making these assumptions. But what does that mean? So what's going on here is, if we imagine a really, if we want, in the extreme case, we want to image the entire sky, which is half of our hemisphere. So if you ignore the N term, you make it N equals 1, you have this just a simple plane, right? And then you have this kind of error offset as you go further away from the phase center. And this error offset becomes quite significant, especially at the edge. And so what you see is, if you were to make an image of the entire sky and not include this effect, what you'll see is in the middle, sources would look pretty fine because that approximation is quite right. Like that plane is quite close to that. The hemisphere, the gap there is small enough. But further away, what you get is that a point source will become smeared out and spread out because you're distributing it all across, because you're not accounting for this W correction. And I guess I should mention, this isn't just about entire hemisphere system. This is just an example of the extreme example. Something like Meerkat or the VLA or a typical dish array, if you're imaging out more than half a degree, chances are you'll have a W term effect. That's noticeable. So typically in the past, people only image small regions of the beam, but now for years we've been pushing the limits of imaging out to full, what they call the full primary lobe of the primary beam, even out to the first side lobe, second side lobe, and beyond. Because we can account for these W terms in an approximate way. You see the fuzzies. Yeah, so given two layouts, so this is a very simple case of two arrays. First, you have some 2D array, so with 3 points all aligned in one, and then one of the antennas offset, or one of the dishes offset. And then you have an east-west array, which all the points are aligned east-west. So this, the first array is only slightly different than the second. And if you compute out the UVW of this, let's just say this is declination 0, very simple. In the east-west array, it's all flat, right? The UV coverage is flat, but in this 2D array, you get 2 lines instead. This is this projection onto this UV space. This is typically what we do. But in fact, it's a bit more complex than that. In fact, east-west is, and these the 2D array are sampling this UVW, and you have to project it onto a 2D plane. And so how you project it produces different UV coverage. We call this coplanar. If there exists approximately a 2D plane, all the visibility measurements can be projected to without kind of affecting the distance between those UV projections. For an east-west baseline that holds that you can see, this east-west, there's some plane at some angle where you can project everything onto, and it hasn't altered. Whereas for this one, there's no 2D, there's no plane that you can pick, because you're always going to be projecting it somehow. You know, this crossover point isn't real in the 3D space, right? But as we project it down, it has to be. So this is kind of the root of the effect that's going on. So what's going on here is that projection on the imperfect projection onto a 2D plane is effectively like taking a dish and moving it in the up-down direction physically, because it's kind of can be seen as a delay offset. So if we have a baseline here that we measure the sky signal from, and then we chuck out the W term, what's happening here is there's some difference between the W from where it was originally to now where we've thrown it out, some offset. And what that means is now we're measuring, even though we've measured this visibility sample, it now appears that we've measured this. So it's as if we've changed the position of the UV sample relative to where it should be. It's a little tricky to kind of think about. Well, you can measure, in your UVW space, given some kind of reference position, there's some distance from that visibility sample to that reference position. And you can pick, say if you have some east-west array, a coplanar array, you can pick a projection where that distance doesn't change. But if you have a typical array, you have to pick some plane. And when you pick that plane, since you projected it, you've changed the distances between all the points to that reference position. So it's as if you've moved the UV sample, or your visibility sample, to a new location. And this basically should introduce artifacts, right? You've moved the position of it. You shouldn't expect it. You shouldn't expect it to not have artifacts. Anyways,
How will those look next?
yeah, I'll show some images soon. But what this is you can kind of think of it as these two things going on. Is that the small angle approximation? We can make a small angle approximation here, and what you can have is basically you can think of it as different phase factors being introduced. So this is our normal phase. This is our normal function. But what's happening here is these extra phase factors are being introduced. And what this is because of your projection, it'll basically take a point source, and the artifact you see mainly is you see this point source, and then you see it spread out, the power spread out instead. Draw some off before and show you. Oh, smart. Okay, yeah. Let's see. Basically, it's a smearing out of a point. And it's most prevalent when you look at a point source, but in fact, it happens at every single pixel. So, given some image, let's say it's a fairly big image that you don't correct for, so you have some point source here, that's fine. At the phase center, it's going to remain a point source. Let's say you have a point source further out here, and then a point source even further out here, in reality. But what you'll see is it'll kind of blur out a little bit. And usually it's typical to see the arc, and then this source will kind of blur out even more. And the amplitude of it will be, the power of it will be dispersed, and you won't see it. And so, in fact, if you have 3 point sources with the same real flux density, what you'll see is this one will be brighter than this one than this one. It's kind of a blurring out. And so, this is with Meerkat, the simulated Meerkat image, is you have a few point sources, and you can see there's a lot of gunk around here, and that's not actually real. So if you can correct for these W terms, I'll show you how we typically do it. And when you do the correction, you see all these really nice point sources going back. This complex, you're not even sure how many sources there are. When you shift, you see, there's 2 sources, but they've been blurred together because of the side lobe and W term effects. You can see this point kind of halfway up. It's quite weak here, but when you do the correction, you see it pop out. Because you no longer just blurring out the flux into the pixels. Okay, so the solutions to this depends on how it's implemented and what science you're trying to do. This 2D Fourier transform is this approximation we're making. In fact, you could do a 3D Fourier transform. That's a perfectly reasonable thing to do. The trick you have to do is you have your visibility space. Instead of gridding to a 2D plane, you grid to a 3D volume, which is kind of computationally, it's going to take up some memory. And it's going to be very sparse, right? You can imagine instead of this 2D projection, your sampling is sparse to begin with, and especially in the volume, it's going to be even more sparse than the 2D projection. So and then you can do your Fourier transform, saying, if you assume that's not an issue, if you're fine with that, you do your 3D transform, and then you have this image, and then you have to do a projection down to an image. Because it's not just L and M, it's L, M, and N, right? And that's fine, you can make some choice about how you want to project it. People typically don't do this. You see this a lot in low frequency wide field imaging. Because your resolution is usually pretty low, so your memory space isn't that big, and it's because of the design of a lot of low frequency arrays are quite dense, and so that means this visibility sampling is quite dense too. So you typically don't use that. Another idea is you use what's called snapshot imaging. So one of the things you can work out if you're really bored one night is that when you're observing with an array, for a given time, all the visibilities are on some plane. And so you can call that a snapshot. Say you integrate for 10 seconds. Every single visibility, you can pick a plane such that every visibility on that 10 seconds is on some plane. Problem is the next 10 seconds will be slightly off and slightly off. So when you have this whole integration, time integration, there's no plane. But every single snapshot does have a plane. So what you could do is you can make an image of each snapshot and then just co-add all the images once you've made them. This is fine to do. Again, not many people do this because each time integration will have a pretty poor PSF, right? Because it's just a snapshot. It doesn't. The whole PSF the whole visibility space hasn't been sampled in, and this doesn't really work very well for deconvolution. And so if you're not doing deconvolution, yeah, you can do snapshot imaging. It's not too bad of an idea. Now these last 3 are kind of always competing, and they come and go in fashion. The first is facet imaging, is that given some large field of view, what you can do is say, instead of imaging that whole field of view, you can image just little sections of it and make a bunch of little images, little facets of each image, of the field of view, and then you can stitch them together later. And this is actually quite, I think, kind of currently the imagers everyone likes right now uses facet imaging, but for a number of years they weren't the biggest, coolest thing. The problem with facet imaging is it's computationally expensive. Instead of making one image, you have to make 100 images and glue them all together. But if you have the computational power to do it, then why not do that? And that, by making smaller images, you're making this small angle, small field of view approximation, and you can just use Fourier transform. You don't have to worry about these W effects because they're approximately, they approximately disappear. These other two, this W projection and W stacking, is basically ways of applying convolutional filters during the gridding operation. These are expensive, computationally expensive in different ways and hard to program. But in typical imagers, there'll be an option of like the number of W planes to apply. And usually an imager will say, well, based on your field of view and your observing frequency and your resolution, you need this many W planes, and you just go, yeah, sure, do that. And it'll correct for it. They're all just kind of, these last three methods are approximate ways to correct for this W term. And it does a pretty good job. And so that image back here, this one is I think it's the W projection. This is the W projection kind of method to go from here to here. And it does it approximately well. And so going back to this whole point I think I made at the beginning was there is usually a correct way to do something. I mean, a mathematically correct way to do something. It just turns out it's computationally too hard. And so instead what you do is you go, well, here's a very computationally nice way to do it, but it's missing these features, and so let's kind of perturb it a little bit and add in what we need as we run into those problems. And then only add them when we need to. And then eventually, if you keep on adding features and features, you get to the mathematically accurate method, nearly approximately. But at some point between the computationally efficient and mathematically accurate is where you want to be. You can say you turn on and turn off features as you go. And that's kind of the idea of these general imagers we use today. Oh, I'm done. Yeah, that's me. So homework should be fairly easy. It's basically it's just writing out some numbers. It shouldn't be too hard. The one point you need to make is that baseline and core baseline, those two numbers are switched, but you'll notice that as you answer it. The idea here is just to work out the resolution and number of pixels for Meerkat based at the different observing frequencies. I can't imagine this should take more than 10 minutes. Yeah, it should be pretty easy. Yeah. Is there any questions? Okay. Yeah.
What's the difference between the optical match filtering and radial match filtering? Is there any difference between them? Or
I don't know too much about optical match filtering. Do they do in optics? They should, right?
No, I mean they use it, right?
Do they? Okay, yeah. It's probably exactly the same, right? They have some image, and then they want to maximize the signal to noise of some object, and we do the same with radio. I guess the difference we would do is that when we make our images, like, in optical astronomy, you start with an image, right? And then you have to do some stuff to correct it, put it to correct the noise and whatnot. But for us, because we've made a coherent observation, we haven't made our image yet. And we haven't gone through deconvolution and it's kind of all these other stages. But still fundamentally the same place. But the fundamental idea is the same. Yeah.
This question true and the conducted one layer.
Oh, yeah.
Let's say for the full layout, whether you can.
Yeah. So so there's this inner core, which is 1 kilometer, and all you have to do is work out those numbers for that, and then instead of doing the inner core, you do the maximum baseline, which is 8 kilometers. So yeah, these are just 2 and 3 are basically doing 1 over again, but let's, in this case, do a different frequency. So you should be 2 numbers here, 2 numbers here, and 4 numbers here. Yeah, I should point out, do this for the full end for the core. So there should be 8 numbers total. Does that make sense?
Why are you giving us the dish size?
So the dish size has a relationship that the dish size is 13.5 meters, and your field of view is related to the dish size, right? The bigger your dish size, the smaller your field of view. So your field of view, you need to compute the field of view. You need, the number of pixels you'll make in your image relates to the field of view. So you should compute your field of view, and then you have some image resolution. Putting those two together, you should get the number of pixels you need. Yeah. Okay. I think this is online too, right?
Yeah, it's online.
Okay.
It's already online.
With that, I'm good. Yeah, unless there's other questions.